Yeah, welcome back to the last topic of our fifth unit, as well as this is the last topic in our syllabus. We are going to see the laser sensor. So we take a laser Doppler anemometer LDA. So it is laser sensor. The optical flow visualization methods offer the advantage that they do not disturb the flow during the measurement process. The laser Doppler anemometer is a device that offers the non-disturbance advantages of optical methods while affording a very precise quantitative measurement of local flow velocity. This instrument is the most recent advancement in the area of flow measurement, especially measurement of high frequency turbulence fluctuations. The operating principles of these instruments involves the focusing of laser beams at the point where the velocity is to be measured, and then sensing with a photodetector the light scattered by thin particles carried along with the fluid as it passes through the laser focal point. The velocity of particles, which is assumed to be equal to the fluid velocity, causes a Doppler shift of the frequency of the scattered light and produces a detector signal related to the velocity. For the instrument to function, the presence of artificial tracer particles is not always necessary, since macroscopic particles normally present in liquids may be sufficient. So that is the LDA introduction. We will see more about LDA. So here, as an example, ordinary tap water contains enough impurities to scatter the incident beam. However, in the cases of glass, it may become essential to insert particles from outside. It is clear that the LDA measures the velocity of scattering particles. Under extreme conditions, particles may not perfectly follow the flow, and therefore there may be errors in measurement of flow velocity. However, if the particles are sufficiently small, the slip velocity between particles and fluid will be small, and thus almost accurate indication of fluid velocity will be obtained. Laser Doppler anemometers have been developed which operate in several configurations of a commonly used mode called dual beam, that is known as differential Doppler, or fringe mode. It is also known as fringe mode. In this, the laser source employed is usually helium neon gas laser, although the argon ion lasers provide a more intense beam output. The helium neon laser operates at a wavelength of 632.8 nanometer. So here the laser beam is split into two equal intensity parallel beams with the help of two coated optical floats. Here a lens focuses the beams at a point F where the velocity of the flow fluid is to be measured. The scattered beam of light moving through the fringe pattern is selectively collected by a combination of lens and pinhole aperture. It is then detected by a photosensor, which usually is a photomultiplier. A light intensity versus time is displayed on a display device. It is oscilloscope. It is the oscilloscope is a device where we can see the display of time versus light intensity. It may be recorded also. The light is simultaneously processed by a Doppler signal processing unit from which the flow velocity data is derived. The frequency f of the electric signals produced by a particle moving across the dark and light fringe pattern with a velocity component v normal to the fringe is given by, that is f, the frequency is equal to 2v sin theta by 2 by lambda, where lambda is the wavelength of laser beam in the fluid. So this can be rewritten as f equal to 2n v sin theta by 2 into uh, 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 lambda naught. Lambda naught is equal to wavelength of laser beam in the vacuum. N is refractive index of the fluid. The The method measures the velocity component perpendicular to the fringe pattern. The fringe pattern may be rotated through 90 degrees to measure the other component of a two-dimensional velocity vector. Simultaneous measurement of several velocity components at a point may be achieved by either polarization schemes using a single laser or two color systems employing two lasers of different wavelengths. So here this is the diagram in next slide. So you can see here this is the laser and it passes through the optical flats. This is the focusing length and lens. Through lens the theta, this is known as cone angle, and through y this is the point of intersection of this laser beam and the scattered beam. So here this is a pinhole and this is x direction, and this is through pinhole the signal crossing unit, through signal crossing unit, and this is the oscilloscope where the waves can be recorded. So this is simple arrangement of LDA, laser Doppler anemometer. So layout, this is the just layout of laser Doppler anemometer, and fringes we can see in next slide. So here you can see fringe pattern. So fringe pattern, this is the wavelength lambda, and particles passing through the fringe pattern, and you can see the intersection fringe patterns through x z axis can be seen like this. So the bright fringes can be observed like this, and this is y direction and this is x direction. In the third direction z you can see like this. So this is the fringe pattern of laser Doppler anemometer. So advantages of LDA, laser Doppler anemometer. This instrument measures the velocity directly rather than by interference from pressure as the case of pitot tube, or coefficient of heat transfer as in the case of hot wire anemometer. So laser is having these advantages. No physical object is inserted into the flow, and therefore the flow remains undisturbed by the measurement. So there is no disturbance of measurement system in the flow. Volume of sensing part can be very small. The instrument has a high frequency response, which is of the order of megahertz. It has very high accuracy, which may be as high as plus or minus 2% of full scale reading. This can be used measurements of flow of both liquid and gases. So this method LDA can be used in both liquids as well as in gases. The disadvantages. So the disadvantages of LDA, it involves the use of transparent channels. This is used for tracer particles for scattering of light beam. The instrument has a high cost and a high degree of complexity. So it is the system, the instrument is the construction itself is a complex one, and these are the disadvantages. When we see the applications, so the applications, investigation of boundary layers and shock wave interaction phenomenon for both laminar and turbulent flows, determination of three-dimensional wing tip vortices near tips of wings of aircrafts, measurement of flow between blades of tube, combustion and flame phenomena in gas turbines and jet propulsion systems, measurement of blood flows, remote sensing in wind velocities. So these are all the applications of LDA. And with this, we are completing the syllabus, and we are completing all the topics in fifth unit. I suppose you have followed my lectures. If there are any queries, you are always welcome to approach me for clarifying your doubts. Thank you, students. We will stop here, and these are the books you can refer. Thank you. Thank you, students. Thank you so much.